Hi, I'm Yi Sun from UChicago, and my talk today will be about the likelihood landscape and MLE for the discrete orbit recovery model. This is joint work with Zhou Fan, Tianhao Wang, and Yihong Wu, all from Yale Statistics. The motivation for my talk today will be the problem of single particle reconstruction in cryo-EM. In this problem, we're given noisy particle images taken by electron microscopes as illustrated on the left. From these large numbers of noisy images, we wish to reconstruct 3D models of the underlying particles. This method is widely used in chemistry and biology, and it won the 2017 Nobel Prize in Chemistry. From an abstract point of view, the problem takes the following form. Given an unknown electron density function, theta star, we take samples as follows. A rotation and projection are applied to the density, and then we record a sample after some measurement noise. From these very noisy samples, our goal is to estimate the unknown density function theta star. There are two fundamental challenges to this problem. First, the orientations of each sample differ by an unknown rotation. And second, the noise level is typically very high, leading to a low signal-to-noise ratio. To address these issues, we abstract the problem into the group orbit recovery model. Let's consider a subgroup G of d by d orthogonal matrices, where for cryo-EM we take G equals SO3. We're trying to estimate an unknown signal, theta star in RD, from noisy observations generated as follows. We take a uniform random element from the group G, rotate theta star by that element, and add Gaussian noise at noise level sigma. This creates draws from a Gaussian mixture over the orbit of the unknown signal theta star. Our model simplifies cryo-EM in two ways. First, we remove the projection step, and second, we'll consider only discrete groups G. These will still preserve the underlying mathematical structure of the problem. To illustrate the problem, let's consider threefold rotations on the plane. Here I've plotted simulated data for unknown signal being the point 1, 0, and the group being these rotations. As you can see on the left, in the low noise regime, 3 distinct clusters remain. Whereas on the right, in the high noise regime, there's only a single large cluster around the origin, and it's not clear that the group has 3 rotations. Our work studies the maximum likelihood estimator for this problem. That's the minimizer of the Gaussian mixture negative log likelihood, as shown. This method was proposed for cryo-EM in the 90s, and it's been implemented in several software packages. It's widely used in both chemistry and biology. The relevant quantities to study for MLE are the Fisher information and likelihood landscape. The Fisher information is the large N limit of the Hessian of the negative log likelihood at the unknown signal point. It dictates the properties of the MLE as well as the local optimization behavior near the unknown signal. The global landscape asks whether there are spurious local minimizers away from the orbit of the unknown signal. This determines whether MLE actually returns a point near the true signal. Let me now move to our results on the geometry of the log likelihood. First, in the low noise setting, we show that the Fisher information is nearly isotropic. This means that it's very similar to the Fisher information for a single Gaussian rather than a Gaussian mixture. For the global landscape, we call the landscape benign if it has no spurious local minima and only strict saddles. In the low noise regime, we show that the likelihood landscape is globally benign for any discrete group as long as the sample size is large enough. For this result, the group orbit structure is important, as counterexamples are known for general Gaussian mixtures. In the high noise regime, the Fisher information is more complicated. we showed that the Fisher information has different numbers of eigenvalues at different scales with respect to the noise. The corresponding eigenspaces are directions of high anisotropy for the Fisher information. To determine the number of eigenvalues d sub L at scale sigma to the minus 2L, we use an algebraic object called the transcendence degree of the algebra of invariant polynomials for the group. That algebra is simply a set of polynomials whose values over each group orbit are constant. Roughly speaking, the number of eigenvalues at scale sigma to the minus 2L is the number of new invariant polynomials which emerge at degree L. One consequence of this result is that the smallest eigenvalue of the Fisher information lives at scale related to the largest degree of a new algebraically independent invariant polynomial. This allows us to determine the scaling of the covariance of the MLE with the noise. This scaling recovers scaling that was found in previous work in method of moments by Perry and Bendera. To illustrate a result, let's consider an example of k-fold rotations on the plane. One can compute to find that the invariants are in degrees 2 and k, and therefore one realizes that the Fisher information has curvature sigma to the minus 4 in the radial direction and curvature sigma to the minus 2k in the angular direction. This explains the oblong shape of the contours around the orbit of the unknown signal in the figure shown. Turning finally to the global landscape in the high noise regime, we relate the global landscape of the negative log likelihood to a sequence of moment matching problems. To state this, let's define the moment tensor of a group orbit in RD as the following expression T sub L. It's a tensor whose entries contain invariant polynomials in theta. We define the moment matching problem opt sub L to be the problem of minimizing the difference, the L2 norm, between the Lth moment tensor of theta and the Lth moment tensor of the unknown signal theta star, subject to all lower degree tensors already matching. Our philosophy is that minimizing the negative log likelihood is roughly equivalent to successively minimizing these moment matching problems. Roughly speaking, our result says that if these moment matching problems have good benign global landscapes, then the negative log likelihood also has a globally benign landscape for sufficiently large sample size. One can check that the moment matching losses are globally benign for k-fold rotations on the plane, which implies that the negative log likelihood also is globally benign. Finally, let's consider the problem of multi-reference alignment, which is very closely related in algebraic structure to cryo-EM. In this setting, the group is cyclic shifts of coordinates of an unknown vector in RD. Algebraically, there's one degree 1 invariant, with the other invariants being split roughly equally between degrees 2 and 3. In this setting, we're able to show that for an open neighborhood of unknown signals, the degree 3 moment matching loss is not globally benign in large dimension. This implies that the negative log likelihood has spurious local minimizers even for large sample size in large dimension. Now let's recall that the landscape was shown to be globally benign for low noise, which means that these spurious local minimizers must emerge as the noise level increases. This is counter to the usual intuition that injecting more noise smooths out the landscape. In conclusion, we studied the group orbit recovery model to illustrate some fundamental challenges in cryo-EM. In the low noise regime, the Fisher information and optimization landscape resemble that for a single Gaussian, whereas in the high noise regime, the situation is more complicated and both are determined by the invariant polynomial algebra. Check out our paper on arXiv at the address below for more, including implications for optimization algorithms such as EM.